Alright, so this is the Efreeti processor. My name is Greg Galloway,
I'm Chris Thomas.
I'm Yungfu.
and we chose the name Efreeti because Efreeti is a mythological creature that is always on fire, and because processors run so hot, we figured it would be appropriate.
I'm going to talk about the instructions for our processor here. We have 17 operations that are supported. All of them are standard MIPS operations, which are listed on the slide clearly, except for CMP, which is effectively branch less than. That's there are three addressing modes that are used by varying instructions. Each instruction only uses one specific addressing mode, but different ones use different ones. The ones supported are basic register addressing, where it's just the values of specified registers are accessed appropriately. Immediate, in which a specific literal is supplied, or indexed, in which case the memory address of the sum of the content of two registers is used. Instructions are encoded as follows. We were originally going to use 1 byte for each portion of the instruction, but that would only allow for 8-bit literals, which is not terribly useful in any realistic situation. So we ended up packing the 32-bit instructions as follows. You always have a 6-bit opcode. We use 5 bits to specify a given register, 16-bit literals, and 10 bits are used for the address in instruction memory of a branch. And in cases where all 32 bits are not needed, the end is padded with zeros. We are using an assembler, which I wrote in C++, which works as described on the slide. Exactly one instruction per line is allowable. It ignores lines that are commented or blank lines, and anything past the first instruction is ignored. So it's a very simple assembler. It works by passing over the text file containing the assembly code twice, the first to determine the locations for branching instructions, the destinations of the labels, and the second pass through actually converts each instruction one by one to a binary file and outputs it. This is our basic pipeline design. It's based off of the basic 5-stage MIPS pipeline from the textbook, modified in several ways to allow for 2 threads to run. Basically, the register file and the program counter and instruction memory and assorted related hardware is duplicated for each thread, and we pass a thread specifier bit through, which just, as you would expect, specifies the first or second thread, and then we basically mux and demux everything appropriately to put it in the correct set of registers and instruction memory, etc.
Okay, so at a higher level, this is our pipeline design. So each of these blocks should represent a VHDL component. And in general, the signals are much as they were in the previous one. However, the state machine tries to manage all the information flow. So you can see that the program counter tells the instruction memories which instructions they're going to be reading. And internal to the instruction memory is a random chance of a cache miss. So on the event of a cache miss, they send their signal to the state machine saying they missed, and the state machine will, on the side, continue to query them, waiting for them to actually give a result and to stop asserting the cache miss signal. In the meantime, it will attempt to run the other thread repeatedly. The same situation applies to the data memory. Both threads share the data memory, and in the same situation they can get cache misses, so it will pay attention to which address is receiving a cache miss. There's 2 ALUs, even though one of them is actually to attempt to ascertain the branches in advance in an earlier clock cycle. They both have the same basic functionality, so they both receive the operands and the opcode, and they both give the results back to the state machine, and the state machine acts appropriately. We have 2 register files, one for each thread, so there will be 32 registers in each register file, and the state machine basically says which register it is looking into, whether it's reading or writing, and the value, and I believe there will also be possibly an enable if necessary, and the registers behave identically, so there shouldn't be any difficult situations there. The test bench is our way of controlling the machine and our way of getting feedback from the machine. So we have it control certain initialization settings, and it also gets information back from the state machine, and we can use assert statements, or we can just view the raw output.
Well, the header, and in our design, there is no write after read, write after write headers, because we just only use integral operations. So for each instructions, there's just one cycle delay. So that means our instructions should be completed in order. That's the reason why in our design there are no.
Yeah, so what he's also saying is that we only execute our instructions in order. So because we don't execute them out of order, and because we use an integer operations only for our ALU, we don't have to worry about those 2 hazards.
Right. Yeah. And for the branch hazard, there's two cases. If there is 2 threads running, that means we can just store 1 thread, and but it's still running. So in this case, the branch header should be eliminated, because the thread can another thread can still continue do the branch computation. So the only hazard will be appear in our design as read after write hazard. If the pipeline control decides there is read after write hazard, we will insert no operation instruction in the pipeline.
Right. So in general, like he was saying, we should have no branch hazards, and that's under optimal situation where we have full access to 2 threads. But in the situation where both threads either branch or only one thread is running, we actually will have branch hazards. So we'll just simply insert no ops until it's ascertained whether it's branching or not, which should only be a clock or 2 delay, a cycle or 2 delay. Okay, so the thread control is managed at initialization, because anytime we're actually running our CPU, we have it attached to the test bench. We allow the test bench to start the initialization, so it will tell the CPU which address in memory to begin executing a program. So initially, when the modules are instantiated, the program counter start by pointing at 0, and they will continue to point at 0. So when they're pointing at 0, they do not increment themselves. But once they receive an external signal saying this program counter moves to this location, then it will begin executing the program. So basically our end program operation would just be a branch to 0, and then it would be the end, because our CPU is giving all the feedback to the test bench. So during execution, the test bench is able to monitor proper CPU behavior, and also we'll be able to view our signals in our memory through the test bench and waveforms. So that's how we control the thread. So when one thread is operating and we tell it to move program counter 2, which might be pointing at 0, to another location, then we'll be able to also make use of both paths through our ALU, or our CPU. And so in our multi-threading control, we have the thread specifier, which is basically a small module that determines which set, as we stated previously, determined which set of hardware to use. So all the duplicated hardware, one applies to one thread and one applies to the other thread. And this is information that will be passed through the pipeline stages. So even though ideally it will be alternating between the 2 threads and giving them balance, if there's a stall on one thread, it will just keep passing forward the non-stalled thread's information, and the non-stalled thread will be able to continue to operate. And so that it goes along the lines of our initialization settings, because it will determine internally which stage of the pipeline